Swayam Prabha. Digital India. Educated India.
Hello and welcome back to this lecture series on foundations of cyber physical systems. So, in the previous lecture we have been talking about different kinds of detectors, and we introduced stateless and stateful detectors like chi-square, windowed chi-square, simple threshold based detectors, and also the Kusum detector. So, we will like to sum over that with this point that there are some limitations that exist with respect to these residue based detectors with constant threshold. For example, a smartly crafted FDI attack can make a system unsafe while also keeping the residue below the threshold. That means, the attacker knows the system model or has an estimate of the system model, and what the attacker is doing is they are injecting just enough impurity so that the residues never do cross. Okay. So, this raises this issue of stealthy attack, which have been highlighted in this cited paper here. So, a stealthy attack, what it will do is, suppose you are given a safety region of a system S and there is a threshold of a detector system Th, and there is an n length attack sequence. So, let us say in the step 1 you have an attack amount AY1 on the measurement and an attack amount AU1 on the controller, and you keep on continuing this attack in this sequence on both the measurements and the controllers, okay, for n number of steps. And this can be successful and stealthy if at some point at some kth step the system state under attack, that is XAK, is no more inside this safety set S, and however, due to all these attacks that you did, what happened is the residue that was measured in all these steps was inside the threshold. Then I would really call it that this is a stealthy attack. So, that is the additional point which one would have to act, that while this is happening, this R k that you are computing for all so this is less than the threshold. So, there is no detection. So, we will conclude this part with an example of stealthy and successful FDI attacks. So, let us consider again the trajectory tracking control system, and there are two states: displacement from the reference trajectory and the speed of velocity, and the speed of the, let us say, the vehicle. So, this is of course not velocity. So, you have acceleration controls over this TTC. That means, you can using suitable control input, you can update the acceleration command of the system. Okay. And let us say these are your discrete matrices A, B, C, and this is your controller gain, and this is your estimator gain, and you have set a threshold of Th equal to 0.04, a very small threshold for the residue. And let us say you are generating attack vectors using this following model. So, you have some parameters lambda, g, and this kappa. Okay. And using, so the parameters values, so lambda is a constant, g is a constant, and this kappa value is changing with this k, right, and an attack you have an attack vector of length n. Okay. So, let us say n equal to 10, and you are running k equal to 1 to 10. So, n is 10, k is 1 and 10. So, all these for these different parameter values of k, you will get different values of kappa k, and accordingly you will generate different values of a k, right. And then using this a k, you can actually you are creating two different attack vectors, one for y, because y is a sensor reading of size 2, and let us say the control input that goes is also of size 2. Okay. So, we are using this kind of a generator mechanism through which we are introducing this much of attack exactly to the y variable and the u variable. So, that is what we are doing here. So, let us understand why we did it like this, because of course, for generating the attack in an automated manner, we would need this kind of mechanisms, because the attack will be inserted in a programmatic manner. So, we will like to give this kind of a relation or something like that, through which the attack values can be generated automatically in the runtime, right. So, we have chosen this kind of a pattern, and using this formula the attack vectors are getting generated. Now, of course, you see that there is some way in which the values are chosen. So, what will happen is with each update in k, this numerator will increase. So, that means this coefficient will increase. That means this coefficient is kind of controlling slowly that how the multiplication factor of the attack vector is increasing slowly. Not only that, you also have k as a power on lambda. So, essentially this is also like an exponential curve increase that is happening. So, you are incrementing two parameters over multiple steps in a nice automated way, using a control over this increasing coefficient, monotonically increasing coefficient, and also a control over this monotonically increasing power value of this constant lambda, right. So, that is why the attack value you see will slowly have an increase, right, a step based approximation of an exponential curve here, right. So, that is how your attack value of y will increase. So, here we are typically showing, although y is multivariate, there are 2 points. Here we are plotting the corresponding norm here, and similarly you have an attack value of these for the attack vector we are actually making the system unsafe, and we are just plotting for the first state, that is the position vector. So, that is not a norm, you are just making the attack on the position vector. So, just as a recap, this is your TTC system we are talking about. So, there are two states here, one is the position, that is the displacement from the reference trajectory, and also the other is the speed of the velocity, the speed of the vehicle, right. So, what we are really attacking is kind of the position value that is really there. We are modifying the position value with larger deviations slowly, and the deviation values are increasing slowly, not at a step I am increasing the attack value by a large deviation, but I am increasing it slowly. And I am not only doing that, in parallel I am also changing the control input value slowly with this kind of deviations. The deviation values are changing like this. Okay. Now, it can be shown that if these attack steps are chosen, what will happen is that for the system you see the residue is always. So, these are the residue values, this is the threshold that has been chosen, and this is the safety boundary of the separation, that is the displacement or the position variable. Okay. And you can see that variable's value is slowly increasing at each step of control, and eventually it is going beyond the safety boundary here, but nobody will detect this attack, because at each point the residues that are getting computed, all these residues are less than the threshold. So, what will happen is that the trajectory control system, its separation from the trajectory will slowly diverge without the residue based detector, this kind of a simple detector even detecting it. And this is precisely happening because I am deviating both the informations, that is the control input as well as the state information, both of them. So, that's an example of a stealthy and successful FDI attack. So, now one may be wondering that, well, what does it mean by modifying the state information? See, the state information is kind of fed back to the controller. So, when the state information is going to the controller, I am changing its measurement. So, changing the measurement is not really changing the actual state, you need to be careful here. So, when the plant dynamics is changing, it is changing based on the actual state, and the plant dynamics is only affected by the modifications in the control input. But when the control input is getting computed, it is what is happening due to these perturbations in AY is the control input calculation process is not aware of the original plant dynamics, but rather it is getting the original plant dynamics plus this AY attack, right. So, essentially it is using a wrong value of state variable to compute the control input, and due to that this state variable value is going beyond the safety boundary. So, essentially here you see that the first state, that is the position, that is what you are able to cross here, and when you are doing the attack here, you are changing this information here. Sorry, I think I told this part wrong. When you are doing the attack here, you are actually, here you have a 0 and here you have a 1. So, that means you are doing the attack on the second information, which is the velocity of the vehicle, the velocity information of the vehicle. So, you are doing the attack on the velocity information of the vehicle, and due to that you are computing anyway a wrong control input, and you are further making some attack on the control input using this AUK, right. And in effect, due to both of these, what you are getting is computed threshold which is below this, a computed residue which is below this threshold, and you are computing this value of state, sorry, you are, I mean this is the observed state of the system, and this observed state is going at some point, it is going beyond the safety boundary that we have set of, let us say 0.2 or something. So, we can understand that this is a really an issue, that if we keep the threshold value as fixed, then it is easy to bypass, right. Now, the question is what can be done. So, of course, there are several things we can do. One example is, one idea is that, well, the attack should be detected as early as possible, because if you can detect the attack earlier, then you can have suitable countermeasures in place. For example, for that point of time you can have encryption on, right. You can have encryption on with less number of samples, because encryption will increase the bandwidth consumption. So, you decrease the periodicity of the loop, that means you run your control less frequently. So, that would mean you are compromising with the quality of control, but still you have a guarantee that, well, whatever I am controlling, that packet, that is a good packet. So, you have a trustworthy control, but at the expense of performance. Okay. So, that would be an option, that I am sensing attacks are happening, let us not forget about quality of control, let us just ensure that the system works without being unsafe. Okay. But at the same time, the detectors cannot be too sensitive, because if I use this as an excuse to reduce my threshold, then what will happen is there may be standard ambient noises in the system, and due to which the measurement errors occur, there was no attacker really, and that would generate a false alarm, right. So, what can be done is, instead of using a fixed threshold detector, one can choose to change the detection threshold over a window length. That means, one can choose to adaptively change the detection threshold by observing the system state under FDI attack. So, you keep on observing the system state and its trajectory whenever attacks are happening, and based on those observations you keep on adjusting the threshold, because you say that, hey, right now my system is in a sensitive zone, I will like the threshold to be small. Right now my threshold system is in a zone where it is much far from going to the unsafe situation, I can increase my threshold. So, using such observations, can I create an AI based or some other technique which will decide when to select which threshold value, so that I have a system where the false alarm rate is not too high and still have a guarantee that my system will never be unsafe. So, let us consider a windowed chi-square detector in place whose detection threshold and window lengths can be changed dynamically. So, let us understand this. What we are doing is, we earlier talked about such windows chi-square detectors. So, you will be comparing a chi-square statistics with a threshold, and we are saying that, well, for this threshold based detector we can change the following parameters. One is the window length, that means how many samples together I should, what is the history of the attack that I should consider for generating the chi-square statistics, this length L, and based on this length what we can do is, we can compute what is the probability density function of this chi-square statistics GK, and this is a standard mathematical formula that comes out from basic knowledge of chi-square statistics, that if the mean is this MLK and the number of sensors considered is M. So, we are generating chi-square statistics for M number of sensors and the mean chi-square statistics is MLK, then we will have a probability density function given like this. So, this is the probability density function which will be capturing this chi-square statistics. Okay. And we can actually check what is that, whether I am less than this threshold or not will be given by this probability density function, will be given by this integration of this PDF, which will be the CDF or the cumulative distribution function. That means, all I am doing is I am I have this chi-square statistics computed. The chi-square statistics will be following this distribution as per the statistics of chi-square. Okay. The properties of chi-square distribution. So, this is how the chi-square statistics PDF will be distributed, and now we need to raise an alarm at certain points. That means, when I go beyond the threshold, then what is the probability that I am below the threshold. So, that would mean that I have to kind of integrate this PDF from 0 to up to the threshold value, and that would give me this function. So, here gamma, this is the gamma function here, just note. So, this is an idea that so we are just putting in these things for your knowledge. Let us not bother about some of these comments here, that this is the typical chi-square distribution that you will have under no attack. So, this is a central distribution. Under attack, these distributions will shift. So, but let us not bother about these statistical properties of chi-square detectors. Let us understand what is important for us. For us, what is important is that for any such statistical detector, you will have two things. One is a false alarm rate and the other is a true positive rate. So, let us understand that what is this false alarm rate and what is this true positive rate. So, false alarm means that there is a detection that is happening, but actually there is no attack that really happened. Okay. And a true positive rate is that there was a detection that happened, and that actually was corresponding to a real attack that happened, right. So, at some kth sampling instance, we can compute both of these things using all these formula based on statistical properties of chi-square distribution that we talked about. So, what we said is, suppose we have taken a L window length detector and it has a threshold THK. So, for a L window length detector, this is how you compute the chi-square statistics GK, and by statistical properties it will follow this distribution of PDF following this function, where MLK is the mean of the chi-square distribution. Once I have known this PDF, I can compute the CDF with like this up to the threshold, and once I have computed it up to the threshold, I can check what is the true positive rate by doing this. That means, I consider that I can be under attack and I may not be under attack. So, when I am not under attack, I will have the one distribution function, and when I am under attack, I can calculate my corresponding distribution function, and when I am not under attack, in this case I figure out what is the probability that I am not below the threshold, right. So, this is how I compute that what is the probability I am below the threshold. So, take 1 minus of that, then that is telling me that I am not below the threshold, but there is no attack here, right. So, I am not below the threshold, but and the hypothesis is that there is no attack. So, that is the ground truth. So, that is why this corresponds to a false alarm, right, and this is how I can compute the false alarm probability in the kth step. I hope this is clear, right. Here we have already used the chi-square distribution statistical properties to compute the PDF, and using this relation, that means integrating the PDF, I can actually see what is the probability that this chi-square statistics that I am computing based on my current observations, that is less than the threshold. So, this is how I compute that, and then at the runtime there can be two possibilities. I am either under attack or I am under no attack. So, in both these situations, if I am under no attack, I compute the probability that what is the probability I am beyond the threshold. So, that is when actually the ground truth is there is no attack, this probability is that of the false alarm, that there is no attack, but still the detector is firing, and in the other case we are saying that well there is an attack and the detector has detected it. So, that is the true positive rate. So, my point is if I am able to compute these distributions under attack and under no attack scenario, and there are mathematical methods for computing them. Computing a distribution means identifying the distribution's mean and variance under attack and under suitable attack models. Once you are able to do that, I can see based on this chi-square detector's window length and the threshold parameter set, that well what is my false alarm rate and what is my true positive rate. Now, in order to improve the detectability, what I will do is I will like to have a higher true positive rate, right. So, the problem then becomes that well how do I choose to have a threshold so that I always achieve this, because this is what I desire, right. So, this leads us to an optimal threshold synthesis problem. That means, I am trying to select suitable values of this chi-square window size and the threshold size, so that my true positive rate will increase and my false alarm rate will go down. That means, this function, that means this subtraction should be as much as possible, right. And they have been weighted with suitable weight parameters W1 and W2 depending on the importance of the attack and the non-attack variables. So, that is how depending on their importance, I mean if I am giving TPR increment as more importance, I will give more weightage W1 here, or if I am giving FAR reduction more importance, I will give a higher weightage of W2 here, right. So, based on this I can create this kind of a threshold synthesis problem, and I can compute based on the probability distributions, and I can compute what is the TPR rate and what is the FAR, and I can create this problem here. Now, a powerful attacker will observe the system's behavior and intelligently they will try to formulate attack values, right. I mean that is how an attacker works, and it is trying to bypass a threshold, right. So, I can create an AI agent game, right. So, what can happen is I can learn a powerful attacker, and then for that attacker I can create an optimal attack synthesis problem. So, what I can do is well what the attacker wants to do is the attacker wants to kind of do a negation of this thing. That means, the attacker does not want my threshold based detector to succeed, right. So, it will have the opposite effect. So, that means, it will try to decrease my true positive rate, it will try to increase my false alarm rate, and it will try to maximize the error between the state estimate and the actual state, right, the estimation error. So, this is how I can model an optimal attacker. That optimal attacker is one who will like to make my detection mechanism bad. So, it will just do the opposite of whatever are the properties of a good detector. So, here it is doing the opposite of that, and it will also try to maximize the estimation error at the same time. So, this is how it is achieving stealth, and this is how in the second component the attacker is achieving what we call as lethality, right. So, using these two components the attacker is becoming powerful, but again the attacker has to be subjected to all my dynamical equation constraints of control, of measurement update, of residue update, of state update, etc., right. So, we can create a complex optimization problem which will create optimal attacks, right. And what we can do is at every sample the threshold detector would choose in such a way that it can detect the worst case FDI attack. That means, we are looking at estimating what is the worst case attack at every cycle dynamically. I am trying to see what can be the attack that can happen, and then toward that I will like to choose suitable values, suitable parameters for the detector. Of course, this is a complex problem to solve in the runtime. So, we can bring in an AI agent. So, I can have a reinforcement learning setup where I have a detector agent, and the detector agent is learning from the affected system dynamics, and it is adaptively tuning the threshold of this residue based anomaly detector, and the performance of the detector is depending on how well it is trained against the optimal attack vectors. And also you can have the attacker agent which is mimicking an optimal FDI attacker. So, let us understand how to build an attacker agent. The attacker agent will try to solve this problem, and the detector agent will try to figure out that well what are the suitable parameters for the threshold based detector, so that this objective function is kind of maximized, right. And once we learn both these agents, deploying them together, I mean in presence of the detector, the attacker agent who is mimicking an optimal FDI attacker, I can learn detection strategies for setting suitable thresholds at different points of the state space, right. So, that is how the performance of the detector will be depending on how well it is trained against the optimal attack vector. So, just to summarize, if I am trying to choose optimal threshold parameters, they should be chosen such that this thing happens, this thing is maximized, right. The true positive rate is high and the false alarm rate is down. But if I have to do that, I have to do that against good attacks, and the way to generate good attacks is by solving this optimization problem. You can try to solve this using some analytical method, or you can have some AI based agent which is mimicking this kind of optimal attacks, and you can have a detection agent which is trying to subvert these optimal attacks by maximizing this function in presence of such attacks. So, that is how you can create a multi-agent RL problem, okay, where you have this attacker agent who is getting rewards based on, so you have this attacker agent who is getting rewards based on this cost function on the right hand side. So, it is trying to learn behaviors between I mean the system behavior, and accordingly it is trying to give suitable attacks on the control and the system measurement, so that this thing happens, this objective function is attained, and at the same time the detector agent will try to figure out what can be suitable window length and other parameters, so that this attack can be subverted. So, we are not asking you to get deeper into this, but what we want you to understand is what is the motivation behind this cost function, how this is modeling, how this equation is modeling a lethal attack vector, and how this equation is modeling a suitable detector. Because what this can help is, if I know that what is a lethal attack vector, for that I can choose suitable detection parameters, so that the detector works more often than not. Okay. So, that is how this variable threshold idea can work by deploying suitable AI agents in a system, and with this we will like to end this lecture. Thank you for your attention.